Hi everyone, how's it going? My name's Dr. Martin Bell. I'm sat here with my dog Gus right now. It's Saturday night here in Sydney, and the last couple of days I've been putting together a little bit of a survival guide related to 5G, and I've become a little bit frustrated with heaps of people sharing stuff on Facebook without really thinking about what 5G is and why it won't bother you and how it will bounce off your skin and the such like. So I'm a physicist. I've got a PhD in astrophysics. I teach at a university. I teach courses quantum physics, computational physics, image processing, advanced maths and physics. And I also teach about 500 to 600 first year physicists, actually non-physicists per year, but they go and study medical science or radiography and such like. And a lot of the stuff I'm going to show you today is straight from that, sit down pal, is straight from that physics lecture, and relating to some of the basic principles about radio wave propagation, how it works, and the such like. So what I'm going to do is I'm just going to pull up some slides to put together. Now, I've been working on this fairly hard, and this is a pretty big job. So just to talk you through what I'm going to talk about, I'm going to spend about 10 slides actually talking about astrophysics, because I'm an astrophysicist and I find it really interesting. But I want to show you that the universe actually produces radio waves. Here you go, go down. Box it, go down. The universe naturally produces radio waves. So if you're worried about what 5G is producing, then you kind of have to have a think about what's out there above your head going on at the same time. As I'm a radio astronomer and I enjoy obviously astrophysics, I thought I'd put a few slides in about that. After that, I'm going to have to get into some basic physics to do with the energy of photons and Snell's law, refraction, and just some of the basic principles of how radio waves propagate and reflect. Then I'm going to get into some of these conspiracy theories and just debunk some of them. And finally, I actually wanted to look at a bit of psychology, to actually look at why people share these things, why people get worried, and perhaps where we should focus more of our attention on, for example, climate change. So I call this thing a 5G survival guide, and this is a basic sort of physics lesson for you. So let's start at the beginning. So what have I been seeing on Facebook? And the first one that got me was this one called Stop the Trials of 5G on the Isles of Scilly and Cornwall. And this one really caught my eye because I was like, what the heck is this? Why are they bothered about this? And in fact, why is this being rolled out in the Isles of Scilly first? But just to put this into perspective, I was born in Cornwall and I used to go on holiday every summer for 2 weeks to the Isles of Scilly. So this one's quite close to home for me. Like, I really wanted to debunk this one because everyone was worried about this. And I was like, oh, come on, let's take a look at what's actually written in that petition. But more recently, since the coronavirus has hit, I've seen a lot of people sharing more 5G stuff, which has been really weird. And it's just also been like, okay, let's just dig into this and have a look. And some of them are really crazy. Like, 5G is worse than the coronavirus. We've all seen these pictures of bees next to apparently 5G antennas that they're not really. And a lot of this has been debunked. But I think if we start from a physics perspective, then you can really start to pick apart some of the arguments these people put together, and then look at the psychology for why people kind of propagate this stuff in the first place, with hoping to sort of put a stop to this, in my opinion. Okay, now the other thing is, this isn't going to be like a 3-minute video you watch, okay, and you pick up in the morning and such like. I've got about 50 slides here, and I've been working most of the weekend to just look at this stuff, and it's massive. And from the physics perspective, it's not massive. Most of this stuff is in a textbook. But what I'm saying is, go and put the kettle on, or go and pour yourself a whiskey, because it's Saturday night here in Sydney. And there's 4 parts to this. So if you want to skip to any of the other 4 parts, jump ahead. But I would advise you to look at the physics part. We have to tough it through that bit to understand why we shouldn't be so worried about this stuff. And I've got some relevant papers about how this all works. Okay, so let's start at the beginning. So what is electromagnetic radiation? A term used so often. Electromagnetic radiation means an oscillating electric and magnetic field, like this example here. So this red line shows the oscillating electric field of light, doesn't really matter which one around it is, and this one, the magnetic field. And this is how we often shorten this to the term radiation, but the bit that goes before it is electromagnetic. Actually, the radiation term often encompasses atomic particles as well. When you split up an atom and produce, alpha decay, beta decay, that also counts as radiation. So the umbrella of all of this is electromagnetic and actually particles. But what we're looking at today is just the electromagnetic part. And of these waves that get produced, like, the waves you get on a beach or from the sea, they have a particular wavelength and frequency and also energy associated with them. So at the low end of this spectrum, we have radio waves and microwaves, and they're very long wavelength, meaning that the length from this peak to this peak is very long. The frequency is very low because it takes more time to move between these two peaks, and they have very low energy, which is really important for the things we'll discuss today. Now, most people would have heard of these terms here: microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. And as we move up to the higher energy end of this, the frequency gets very high, the wavelength gets smaller, and they get very high frequency. And the difference between the radio to the gamma rays is really important because it makes a massive difference to the properties that you see within those electromagnetic waves or radiation. Okay, so here's another way of looking at it. I'm just going to move my bit up here. So the radio waves, let's look at the typical size and compare them to something we understand. So a radio wave, like the really long wave radio stuff, is the size of buildings. Like it's a huge wavelength, meters, 10 meters, 20 meters. And as we move up into the microwave, they get to a couple of centimeters, and the sort of millimeter waves, which we'll talk about today, a couple of millimeters. Infrared, like the point of a needle. Visible light, hundreds of nanometers, starts to get to the size of these protozoans, which I'm not quite sure what they are, but sort of cellular size. Ultraviolet becomes a wavelength around the size of molecules, X-ray atoms, and gamma rays, like actually the size of atomic nuclei. And that's really important. Now, if we were just to look at the temperature scale of these things, radio waves would be typically really cold because they're low energy. So like the equivalent temperature of a radio wave would be very low at minus 272 degrees Celsius. Whereas if we go to the other end of the spectrum, to produce X-rays and gamma rays via thermal emission processes, you need like 10 million degrees Celsius. So something really, really, really hot. Now, okay. So the two ways we divide this up then is based on the properties of these electromagnetic waves is non-ionizing and ionizing, okay? And the ionizing part starts to kick in around ultraviolet, X-ray, and gamma ray. And that's because what ionizing means is it starts to interact with the actual atoms and molecules in your body because the wavelength approaches those sort of sizes. Whereas the non-ionizing end just don't have enough energy and enough punch. And they're also really big, like it's something the size of like me or the house or the room. I mean, interestingly, if you look at really low frequency radios, when you had those old radios in your car, the wavelength they would pick up would be meters to 20, 30 meters, something really, really long. And actually at those wavelengths, the radio waves see things like the size of mountains as obstacles. And that was actually in the design, that around the side of edges of mountains, these radio waves would diffract and be able to move into valleys and propagate the signal better. So as we move to different scales, like when you're in radio waves, like millimeter to centimeter to meters, the properties are like kind of different compared to the ionizing end, which can really start to interact with the things in your body. And the definition is really, really important. Okay, so if I go to the next slide, the other way to kind of look at it is good and bad, right? So the good end is, things that won't bother you, and the bad end is stuff that starts to give you cancer and really interact with with the sort of stuff in your body. Now, I'm going to move this down. So, as a scientist, can I say this to you right now? Because there seems to be a lot of claims that microwaves can cause cancer. We'll look at that. But let's just say this clearly. Electromagnetic radiation causes cancer. It's the UV, the X-ray, and the gamma rays, the ionizing radiation, which does this, okay? And that's really important. And we're not lying about it. Like, if you ask any scientist, you know, people go, oh, these new 5G is going to cause cancer. We're like, no, it's not, but bloody UV does. Like X-rays do and gamma rays do. Like, be really careful. And we've lost good scientists to this, because Marie Curie was one of the first person that, you know, discovered radioactivity, radiation, and got exposed to a lot of gamma radiation and lost her life through cancer. So we're well aware of this. It's just that we have this defining point about where the ionizing end of this spectrum is, and where the low end of this spectrum is as well. And I wanted to tell you a story here about the Radium Girls, which is kind of an interesting story about a group of women that worked in in manufacturing in the turn of the century, something like this, when radioactivity had sort of been just discovered. And if you took, I think it was radon or some sort of paint with a high radioactivity, they would paint this onto the tips of watch hands, and it would glow in the dark. But what happened to them was to paint these onto the watch handles, they used to lick the paintbrush and then put the paint on, which meant that every day they were ingesting this radioactivity. And most of the young girls died from being exposed to that, being exposed to that radiation and ingesting it into their body, and sued the company. And it was one of the first sort of libel suits of being exposed to radiation. And let me be really clear as well. I'm an astrophysicist. Let's talk about the sun. The sun produces a big spectrum of emission from radio up to X-rays. Luckily, the X-rays and gamma rays are typically removed by our atmosphere. We've got some shielding against them, but the UV's not. And the UV's ionizing, and it hits your skin, and it causes cancer. There's no scientist or medical practitioner that's in dispute about this, which is why we say when you go to the beach, like, put sunscreen on. It's really important. And be really, really careful. So a lot of these analogies, when you get to 5G and you say, well, you know, 5G might heat your skin a bit or do something like this, you know, some biological effect that might happen. It's exactly the same when you walk outside and you're exposed to the sun. You're being exposed to radiation, and we're telling you it's ionizing radiation, and it's not good for you. And it does cause cancer, and we have proved it. And there's every paper under the sun and entire industries that go, you know, that work to try and stop you from getting that and put this sunscreen on. So it's kind of hilarious when you see that that radio waves are really bad, and you're like, whoa, you know, put some bloody sunscreen on when you go to the beach. Anyway, so that's a bit of history of the sort of bad end of the electromagnetic spectrum. Let's do some astronomy for a bit. Okay, so I'm a radio astronomer, which means that I work in the radio band. So I actually use radio waves that are produced out in the universe, in our galaxy and beyond, to take pictures of the universe and to study it and to do the physics. And initially, about 100 years ago, astronomy used to just mean optical astronomy. It just meant the stuff that you would do with your eyes or with a small telescope. Sorry, excuse me while I have a whiskey a second. Now, in the 30s, it was found that there was, when it was, I think it was during the war and around that time, that they were developing radar, and they looked sort of, as the night sky moved around, they noticed more static that would get sort of brought into the receivers they were using. And they actually discovered that the galaxy itself was producing a lot of radio waves. And since then, astronomers have completely branched out from being optical astronomy. When radio astronomy was first developed, we had to call it radio, then optical. And then we found X-rays and then ultraviolet, visible. To be honest, now we study the universe across the entire electromagnetic spectrum. So when you talk to an astronomer, they might specialize in a particular waveband. And my speciality is radio. I've got a little picture here. I came to Australia probably 10 years ago now to work with the telescopes down here, which look like this. So I started coming over here to work with a number of telescopes. Back in 2007, I started working with the Australian Telescope Compact Array, which is pictured here, which is 625-meter antennas on a track up in Narrabri, about 10, it's about 10 hours drive from here. And you can collect radio waves into that dish and use this array to make images of things in outer space, which I'll show you in a second. Since then, what I was also interested about 10 years ago was I worked as in my master's degree as an antenna engineer, which is developing the receiver technology and studying the electromagnetic properties of these dishes to improve them and calculate how scattering works and reflection and all the rest of it to help design them better. But actually, I did a master's degree in Sweden, and then I moved out to Tokyo Institute of Technology at Ando Hirokara Labs. And in that team there, at the time, they were developing broadband 4G and doing some really, really cool antenna engineering, which is why kind of when it comes to the 5G side of things, I remember back 10 years ago when they were developing 4G, and I'll talk about that a bit more in a second. In the last couple of years, this left-hand telescope is about 25 years old, and we've just built the Australian Square Kilometre Array Pathfinder. This is about a $200 million instrument that has a lot of amazing phased array feed technology in these focal points here, which act as like a radio camera. It's really, really cool new technology, which we can do some better stuff with. And the reason with the radio telescopes we have lots of these spread around is that it's kind of helps improve our resolution and gives us different sort of pierce points to look at things in space. Okay, so this is really important when you start to worry. Let me just try and make myself smaller here, trying to keep out of the way. That should work. How about I go down there? This is really important, and I think the sort of hippier people on these feeds will kind of find this interesting, is that everyone's going, wow, we're being exposed to radio waves and we need to get rid of 5G and 4G and whatnot. You are being exposed to radio waves right now from the stuff above you in the universe. And there's a couple of mechanisms for how this happens. And look, the power is very low. We need these big antennas to collect them. But for some of the cases, it's not crazy low. So I'll talk to you about the cosmic microwave background radiation, which is this sort of image here. This is the afterglow sort of heat of explosion from the Big Bang, and it's sort of cooled to very low temperatures. And here we can see these anisotropies, they're called in it, these hot points and colder points, which gives us clues about some of the cosmology of the early universe. But if in your old sort of analog television receiver, you tuned to sort of a fairly correct frequency, you would, about 1% of that static you would see on that screen would be caused by this cosmic microwave background radiation. So you're constantly being irradiated by these. And I kind of want to call these natural radio waves, you know, because everyone's going to go, well, those are natural, so that's all fine. There's nothing different between natural and man-made radio waves. They're exactly the same thing. But nonetheless, you're still being irradiated by these as we speak. The other one, which is pretty remarkable, is called the hydrogen line. And this is just incredible, I think. Hydrogen, a proton and electron, the simplest atom we have in the universe, the first thing that would have been made after the Big Bang, none of these complex molecules like, you know, even helium or carbon or nitrogen, the most basic building block we have, naturally produces radio waves. And the term's quite long for it. It's the way it does it is with a quantum mechanical spin flip transition, which is basically the spin of the electron and the protons here sort of moving down into a different spin state. And it does that about every 21 million years. it's quite rare. But basically, there's so much hydrogen out there in the universe that this is a booming signal which we can use to study the rotation and evolution of the universe and do really, really cool stuff with it. So I've got these images of nearby galaxies taken in H1 in hydrogen, mapping the content of this hydrogen. And during my bachelor's degree, I actually sat on a rooftop in Cardiff with a very primitive radio telescope, like a 3-meter radio telescope and a hydrogen line spectrometer. And you could actually map the rotation of our own galaxy by using the fact that we knew exactly where this this hydrogen line arrived, you know, in the right frequency. And that actually led, the first rotation curve studies as they were, led to the first ideas of dark matter, because when you look at the rotation profiles of our galaxy, it doesn't add up and there's a lot of missing mass there. So the hydrogen line's so important. And it's such a cool thing for radio astronomy. Like, it's one of our main things we really do is a lot of hydrogen line work. And we're so lucky as well to have, the most abundant element in the universe produce radio waves naturally. And the other one, which I work on much more often, is synchrotron radiation. And that's spiraling of electrons in a magnetic field that then produce radio waves at a variety of frequencies. And this is one of my favorite objects here on the right, which is SS433, which is a supernova remnant, but also stellar mass black hole. So in this little blob thing, somewhere in there is a black hole. This object has exploded. It's an old star or something. And it's exploded, and then the magnetic fields have twisted this thing into like this weird corkscrew feature, and it's all produced synchrotron emission. So synchrotron radiation allows us to study the surroundings of black holes, and I'll show you a massive image I've produced of hundreds of thousands of supermassive black holes. Okay, let's go back. Okay, so that's actually my next slide, is that we can observe black holes with radio telescopes via radio astronomy. And on the left here, I've got a galaxy. I think this is Cene, might be Cene. Anyway, it doesn't really matter. So what we've done here, and the black holes are really weird. Most people think that nothing can escape a black hole, but that's true. But black holes are so dense that they're so aggressive to their surroundings, okay? So they suck a lot of material in. And for reasons we're trying to understand now, they produce these huge plumes of jets, of material, pushed out on this bipolar sort of structure that spread out in huge, structures into the interstellar medium. And this is an example here of an overlay. So what you can see here is the optical starlight. So a lot of optical light that we've taken with an optical telescope, a mirror-based telescope. And then we've overlaid the radio emission from this. And you can see these huge pluming jet structures being punched out from these. And here's another galaxy 3C31. And this often kinks and bends around depending on a lot of structure from the interstellar medium. Here's a bit of an artist impression down here. Anyway, the point of this is that, we know a huge amount about the universe from just studying the radio waves that they produce. And there's a lot more objects that I study day to day. Flare stars, brown dwarfs flare up and produce a lot of radio waves. Black holes, active galaxies, big supermassive black holes and small supermassive black holes are candidates for producing radio emission. Big giant blasts, gamma ray bursts, radio supernovae, gravitational waves produce these radio waves. Jupiter is actually a big producer of decimetric radio emission, and we think that exoplanet stars around other planets around other stars will produce radio emission and bursts like this. One of my favorites is a tidal disruption event, is where a star gets too close to a black hole, gets ripped apart, goes supernova, material gets dragged onto the black hole, produces the radio jets, and then we see, with a lag of a couple of days, this big radio emission that's produced after it, and there's neutron stars and other things. Anyway, there's a whole zoo of things we can study out there in the universe that produce radio waves, which are radiating you with radio waves right now. Okay. Right, so more recently, this is the last astronomy year, I've been working with a very special low frequency telescope in Western Australia. I've actually been out onto site to help plug things in and build this thing. And it consists of these weird sort of spidery dipole antennas, which act as our kind of dishes that I showed you earlier. And these things need to be quite big because they're collecting very low frequency radio emission. And all of these tiles sit out there in the desert, and we correlate them all together to produce very wide field images of the night sky in radio. And I'm just going to stop there and show you an actual map that I've produced with this telescope. So, okay, let's have a look here. So this is the southern hemisphere. If this was a projection of, the equators, where the equator is, and I projected our coordinate sphere for longitude and latitude out onto our celestial sphere above us, this red line would represent our equator here, our zero declination, and everything in the southern hemisphere is down here. And every white blob in here represents an object that's emitting radio waves. And also, most of these objects will be supermassive black holes, like the ones that I just showed you previously, with these big pluming jets. Just this telescope's not, it can't resolve these jets very well, so it represents them as a bit of a point object. And this big patch here is the galaxy, and there's other big old exploded stars and other sort of things going on in here. So this is quite an old image now. But anyway, the point of showing you this is to say, look, this is kind of what I spend my days doing, is working with radio waves and trying to make images of the night sky to understand the physics of those objects. And to do that, you have to have an understanding of the antennas and then the circuitry to take images of these things. Okay, right, that's the astronomy part. So let's now take a basic course in physics, if we may. So what's important for us now is to consider some physics. There's a lot going on this slide, but I'll explain it very briefly. Snell's law and the law of reflection tells us how any electromagnetic wave will reflect when it hits the surface. And there's a couple of important parameters associated with that reflection. Here's an example here where I have some light ray, if you like. We'll do this in terms of light, but the principles stay the same for radio waves. We just have to change the wavelength. I have a light wave moving into a box here. As it moves into a different medium, okay? It refracts, and then as it moves into this medium, it can undergo total internal reflection and then refract out. And the parameters which control how all this works are these numbers called the refractive index here. And importantly, there's a really important point to understand what this refractive index does and how we work out the reflectivity and such like. Now, if we think about it, I said earlier we have this electric and magnetic field. And that's like, the magnetic field is like getting a magnet and just sort of wobbling it up and down. Now, that's fine if I've got a magnet in free space, which means that like there's nothing near it, it's in outer space, there's no other magnets near it, then it can wobble around really, really easily. But then as it gets to some sort of medium, like, glass or water or something like that, there's actual molecules in those water which have some magnetic properties which might slow down and impede the motion of that magnetic field in that substance. So the refractive index, which tells us how the reflection and transmission of these waves in this material work, is the combination down here of what we call the permittivity and the permeability of that material, which is the ability for that electric and magnetic field to move through it. Another analogy would be, if I was swimming in a swimming pool, I can swim in the swimming pool, but then when I reach the boundary, the concrete, everyone will go, well, that's a solid. And if I was representing it in terms of these values here, I would suddenly change those values and go, well, you can't swim in that. And that's exactly how the electromagnetic wave views this. And for our simple model here, this can explain a little bit like the surface of our skin. We can model how we look to a radio wave and how the sort of refractive indices and these values work to tell us how much something will reflect off that surface and how much we transmitted in. And that's really important for worrying about 5G. Okay. Now let's talk about the photoelectric effect. So Einstein, most people will be familiar with his theory of relativity. So I'm just going to pour myself another whiskey while we're talking here, because this is going to be quite a long talk. Okay. So Einstein is mostly famous for his special theory and general theory of relativity. And what most people don't understand is that he actually won the Nobel Prize in 1922 for a thing called the photoelectric effect, which was a precursor to quantum mechanics, or it was one of the experiments needed to explain and sort of move forward with quantum mechanics. And the experiment looks something like this, and it's really important for considering if 5G is going to be harmful to you. So you get a battery pack here, and you connect it to some metal plates. Okay. Now, you know, if I walked up to you in a pub or something and I said, I've got these metal plates, and can electrons move? Can a current flow between these two plates? You go, well, no. You need to connect a circuit with wires for it for the current to flow and a light bulb to switch on and such like. And what Einstein actually was able to explain is that if you took these plates and you shone UV light on these plates, you could then record a current between those two plates. And that's fundamentally important because when the UV electromagnetic waves hit this surface, they have so much energy and punch, they're capable of releasing electrons and causing the current to flow, being absorbed by the other plate at the top. And that only happens when we get up to UV, sort of UV X-ray and gamma ray strength with the type of light. And this is like HSC A-level physics. Like I did this at Truro College. We connected two plates and shone UV light on it and then measured the current. And it's a very particular point when you increase the intensity of the UV or vary the wavelength that this current starts to flow. And that's because it takes a certain energy to release the electrons from this surface. And that's really, really important because that's where our definition of ionizing and non-ionizing comes in. The ionizing part is the releasing the electrons, where the electromagnetic wave can actually do something to the things in your body, like release electrons and interact with it. Okay. So unfortunately, we need to do a bit of maths now because most of the people on the forums, you know, Facebook, whatever, go, well, 5G is going to be way more energy than 4G. So let's actually look at the numbers. So the way we count the energy, it's the simplest equation. And again, in my first year physics course, for non-physicists at university, I expect them to do this calculation, and this will be an exam question. And we use a very simple equation to calculate the energy of any electromagnetic wave. Doesn't matter what it is, we use the same equation. And the equation is E equals HF. And this is called Planck's law. And E equals HF looks like this here. And it's the simplest, it's the simplest equation we can get kind of in physics. It says that E, the energy of the electromagnetic wave, is equal to H, which is simply a constant, multiplied by the frequency of the electromagnetic wave. So let's do an example for 4G. We'll take frequency is equal to 2.1 gigahertz. So we'll say the energy is equal to, so Planck's constant is a very small number. H is equal to 6.63 times 10 to the minus 34 times 2.1 times 10 to the 9. So that's 2.1. And gigahertz means 10 to the 9 cycles per second. And the energy that we get out for one, what we call a photon, or as one packet of those radio waves, is 1.4 times 10 to the minus 24 joules, like a really small amount, like 1.4 times 0, no, it's actually 0, 0, 0 times 24 zeros, 1.4 at the end of all of that, okay? And that's the energy of a 4G photon. Right, so let's do the same calculation for a 5G photon, for 5G radio wave. And F equals 50 gigahertz in this case. So we plug the same numbers in. I hope I've got my numbers right here. I think I have. This is me scribbling this down. Equals HF, 6.63 times 10 to the minus 34, 50 times 10 to the 9. And we get something, which is an order of magnitude bigger, right? Okay, this thing's 5 and that thing's 2. That's a little bit bigger, 3.3 times 10 to the 23. So let's divide the energy of 5G divided by the energy of 4G. And The energy of 5G is 23.7 times more energy if you assume 50 gigahertz. Now this might go up to 100 gigahertz, so just 40 times more energy. And like loads of people use this as evidence online. They go, "Whoa, it's 40 times more energy," and a physicist would go, "Ah, come on, so what?" It's not that much more. So let's look at an X-ray photon. Now, an X-ray photon has a frequency of 3 times 10 to the 19 hertz. And if you bung this in, 6.63 times 3 times 10 to the 19, you get 1.9 times 10 to the minus 14 joules. Still something that's very small. If we divide the X-ray by the 4G, or we do it with the 5G if you want, you get that it is 1.4 times 10 to the 10, or 14 billion times more energetic than the 4G photon. And that's really important. And that's why, so in this game, times 2, times 3, don't care. Times 10, times 100, okay, times 1,000, 10,000, now you're starting to get to the energies that I really, really care about, okay? So 4G, 5G, it's still so low energy that it's, in terms of comparative terms to the ionizing radiation, it's really not worrying about. So I love it when people use that argument, because you're just like, well, that's just rubbish. Who cares? But we'll look at a bit more of the properties. Now, the main point is as well is to consider the properties. It's not just the energy that's changing as we move to the higher frequencies like the X-rays. It's that they get smaller as well. So they can actually interact with our body. Whereas a 5G radio wave, is, it's just on a spectrum of radio waves. It's still only a couple of millimeters or centimeters. It doesn't really matter. It still sees your skin as a surface to reflect off. Okay. So, pyramid of physics and technology. Now, the laws that I've just shown you, the photoelectric effect, Planck's law, and many others, form this kind of pyramid where underneath a lot of other industries and technology and engineering lie these equations. And it's really hard to pull them out. So when I want to argue with someone like, someone goes, blah, 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 blah. You have to attack these equations and show me how they do not work in other different scenarios, right? Because this is textbook stuff. This isn't stuff where I go, oh, a study was done and there weren't many people involved with it. This is stuff you measure in a lab, and it's stuff that's taught in the textbooks, and it's been around for hundreds of years. And on this pyramid of things that we build, you have the underlying physics, and then we engineer things with it, and then we build technology, out mobile phones, the internet, and then people go, well, scientists don't really understand how radio waves work. And that's hugely ironic, because you're sat there with a mobile phone going, oh, do scientists really understand how they work? You go, well, you're bloody using one. It's kind of ridiculous that you go, well, yeah, a radio wave's still a radio wave. So, they're non-ionizing, don't worry about it. And I don't think people appreciate this. They try and argue with you, and you go, but it's like someone saying, no one knows how a car works while driving around in a car. No one could build a car whilst driving around in one. You're like, you're in the car, so clearly they've built one and they understand how it works. We apply all these equations when we develop this technology, which you use to argue about it, ironically. Anyway, just a bit of an observation. Okay. So let's look at some scientific studies, and there's heaps of them around, and we'll look at some conspiracy theories in a minute. So I really like this paper, and there's a couple of things to note about this paper. Excuse me. The first one is IEEE, which is I've got it written down on the next slide actually, but it's the main standard for journals that we submit articles to for electrical engineering and electronics. And when I was studying antenna engineering years ago, this IEEE was the one you went to. You're going to have access to the journals and anything in IEEE, you just go, okay, great, that's good. So this person's written for Ting Wu, and it's called The Human Body and Millimeter Wave Wireless Communication Systems, Interactions and Implications. So they look at the interactions of millimeter waves with the human body, and there's this very basic kind of diagram here, which we looked at in Schnell's law. Reflection, transmission, and if I go to the next slide here, what they do in this paper is develop a model of your different layers of skin, clothing, skin, I'm not sure what SAT is, muscle, okay, have different refractive indices, different dielectric properties as the radio wave propagates in. And this is kind of what I spent a year doing, not with the human body, but when I was in Tokyo for a year. Computational electromagnetic engineering is taking these equations and applying them to predict some outcome from some antenna system that you have. And you apply a number of these equations here to calculate, what would happen as this interacts with your skin or the such like. And you'll notice here we've got these permeability, permittivity factors. Now, this is the really important point from this paper, which I thought was really brilliant. And I was cracking up when I saw this. This plot here shows us the penetration depth of of radio waves, or 5G, if you like, in millimeters. So this is penetration depth to 1 millimeter and to 6 millimeters, and a function of frequency. So 5G operates from 50 up to about 100 gigahertz. And what you'll notice here is that the penetration depth for 5G is actually lower than it is for 4G. So when you moan and go, oh my God, 5G is more energetic and it's going to get into our bodies and do heaps worth stuff. Actually, the penetration depth's a lot lower. You should worry more about 4G, which can penetrate up to, so 4G is actually a bit lower than this 10. It's 2.4 and 5 gigahertz, so it's down here somewhere. But this trend will continue, as noted by the papers that I'm going to show you in the next couple of slides. So the take-home message is 4G will penetrate further into your body, not 5G. And I think that's pretty important to note when we start reading some papers on this sort of stuff. Okay, let's see what we got up next. Okay, so I don't know where I can move myself here. I'm going to move myself in front of this guy. So there's this paper. So what does the Institute of Electrical and Electronics Engineers, IEEE. So these are the guys you go to say, hey, look, I'm doing some blah, 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 electromagnetic engineering, or now this waveguide works, and you go and look at their papers, and and we trust they've got a high impact factor. They've got 500,000 members around the world, and we trust what's published in them. And it's actually these guys that publish the work related to the safety standards for 5G and radio wave. And actually, a lot of them are very cautious. But nonetheless, they say, look, you should probably do this, and you should keep under this level and such like. So I want to read you this paragraph here. And this was the paper that was released in 2019, and it's called IEEE Standard for Safety Levels with Respect to Human Exposure to Electric, Magnetic, and Electromagnetic Fields from 0 Hertz to 300 gigahertz. Now, that's low frequency radio waves, right up to 300 gigahertz, almost infrared. That's like the whole thing, okay? That's not like we're not differentiating like any of our radio wave spectrum. And actually in this paper, if you go and look at it, which I have today, very tediously looking through this, it's very long, and you can go and read in there like all the nitty gritty details about, radio wave exposure. But let's read this paragraph here. Examination of the literature on exposure to electromagnetic energy revealed no reproducible low-level adverse health effects. Moreover, the scientific consensus is that there is no acceptable theoretical mechanisms that would explain the existence of low-level adverse health effects. Since the publication of their previous document, advances have been made in the scientific knowledge of the biological effects of exposure to electromagnetic energy. This additional and cumulative knowledge helps strengthen the basis for the confidence in the assertion of these ERLs. These are these levels that they're producing in this. The literature review also evaluate the possibility of adverse health effects associated with chronic low-level exposure. So that's just not just the stuff around the house, or live on a farm out in the middle of nowhere, sort of low-level exposure. For exposures to electromagnetic and electromagnetic fields at frequency 0 Hertz to 300 gigahertz, the following two conclusions were reached. The weight of evidence provides no credible indication of adverse health effects caused by chronic exposure below levels specified in this document. No biophysical mechanism has been scientifically validated that would link chronic exposures below levels specified in this to adverse health effects. Based on the collected findings of recent reviews, the weight of evidence continues to indicate that chronic exposures at levels specified in the standard is unlikely to cause adverse health effects. And the subcommittee continues to routinely evaluate new research and will, if appropriate, initiate revision. And I think that's really important to note that we're still very cautious on this, and most of the wording will say, look, we've got no reason to think, we can't prove that this doesn't cause blah, but stay below these levels, and really, like, we can't find anything. And I'll talk about that a bit more later. Everyone goes, well, you know, it's like, come on, guys, like, we've overturned a lot of stones here. And for me, this is one of the major papers and papers they're in, and loads of other papers that I've read as well, which just go, don't worry about it. So anyway, I trust these guys, and this is the paper you should read. Right, so to the conspiracies. So I started seeing this pop up about 18 months ago, maybe a year ago. And it said, stop the trials of 5G on the Isles of Scilly and Cornwall. And right, so I grew up in Cornwall and I used to holiday at the Isles of Scilly. So I was like, oh, for God's sake, what is this about? And I've looked at this petition and I want to pull it apart sort of piece by piece. I don't know who's written it, but there's heaps of this stuff on the internet, and it's sort of gaining momentum weirdly. And, you know, this is why I'm making this video today, to say, well, what the heck's this about? So let's pull this petition apart and let's see if we can have a look at some of the claims that it makes. So it says there are over 10,000 peer-reviewed studies which are mostly undertaken on 3G and 4G technology, which show that there is a risk of harm to humans, flora and fauna, on levels significantly lower than the International Commission on Non-Ionizing Radiation Protection Guidelines. So I looked these guys up. These are actually different from the IEEE people. And I actually went on this website and I was like, okay, who are these guys? And there's a whole section in this which repeats pretty much what the IEEE say, which says, after several decades of RF-EMF research on numerous potential health effects, the only substantial effect RF-EMF exposure relevant to human health and safety is heating of exposed tissue. RF-EMF can penetrate into the body. Now, this is important because this is what we showed in the previous graph. The higher the frequency, the lower the penetration depth, and cause vibration of charged or polar molecules inside. This results in friction and thus heat. Now, anyway, well, there's plenty of literature to say, look, don't worry about this, but it does produce some heating of your skin when this penetrates. Now, my analogy for why not to worry about this, people go, well, you know, what can the heat do and stuff like that? Well, heat's heat. When you go and lie on a beach, you're getting heated by infrared, optical light, and UV light, which we know is carcinogenic, which is why we ask you to put sunscreen on. So if you think this is a gotcha here where they go, well, it's going to cause a small amount of heating, yeah, sure, millimeter waves will cause a little bit of heating as they penetrate your skin, but it's not going to penetrate below your first couple of, you know, millimeters of skin. And that's the real catch-up for me, where I go, well, when people are saying, right, it's going to cause cancer, it's going to do this, and it's going to do that, I go, well, how does it get in? And the other sort of really hilarious point about thinking about this is, I typically ask people, can you see me? Which the answer is yes. And I was like, well, that's because light bounces off my skin, which is higher energy. If light bounces off my skin, and reflects a lot of it, and so there's radio waves. And in actually our antenna engineering, we use this fact. Some of the guys in Tokyo were designing antennas that the entire purpose of them were in the design of railway stations. And they were using humans as reflectors to reflect the radio waves down to points of the station where they didn't want to put additional transmitters to keep the power lower. So you just use the human as a reflective body to propagate the radio waves. So anyway, that was one of the first points. And they're over this number, 10,000, you know, it's like, come on, guys, like, I can find a large number of papers that sort of argue the opposite. So I'd love to see them. Okay. So this guy is interesting. So in 2018, Dr. Martin Paul released his damning 90-page report, 5G, Great Risk for EU, US, and International Health. Compelling evidence for 8 distinct types of great human harm caused by electromagnetic field exposures and the mechanisms that cause them. Okay, so let's have a look. And actually, if you look this guy up, he's got a PhD, he's an emeritus professor, and you kind of go, oh, okay, all right, let's have a look at this thing. Now, this is something I took from a website. I'm going to jump on to the next slide because when I Googled this guy, this is quite worrying, because I Googled this guy, and the second thing that came up on Google was, Professor Martin L. Paul does not know the basics about millimeter waves. Now, my analogy here, if I'm trying to sort of, you know, look at all this evidence and sort of work out what's what, if I look at a person and say, okay, does this person look like a legitimately, you know, good researcher? And I Google them, and the second hit I find is someone writing an entire web page saying they don't know what they're talking about. I'm a little bit worried at that point. And for example, if you had cancer and you were getting cancer surgery, and you go, right, I'm going to check out how good the surgeon is. And the second page of your Google hit says, this guy doesn't know how to do cancer surgery. I'm a little bit worried at that point. And some of this guy's claims state that in 2 years from now, if wireless networks will not be switched off immediately, people will become sterile and reproduction of humankind will cease. In 5 to 7 years from now, human brains will degenerate to the degree that normal functioning of human brain will cease. Taken from that website. So I had a look at one of the guy's papers and I was like, yeah, right, like this, just I couldn't make head nor tail of it. So the jury's still out on that one, but in terms of the more credible sources out there, this is one of the better ones. We're going to look at more of the crazy as we go through this. So I'll leave that one alone. And the last part of this petition says, stop the 5G rollout and provide peer-reviewed scientific evidence proving there is no harm to human health and to the environment. So I'm saying, sure, please read the IEEE standards for safety levels with respect to human exposure to electromagnetic fields, 0 to 300 gigahertz, and references therein. Because you've got to deal with that one. And we're going to talk about cherry picking, and we're going to talk about how to cleverly write one of these petitions so that it seems like there's a lot of compelling information out there about this. Now, okay, here's a little ramble about something else. So this is the Large Hadron Collider. Let's talk particle physics a minute. And the title here is Scientists Constantly Update and Test Their Ideas. Now, do I really want to go online and say, there's absolutely no mechanism that can do this and you shouldn't worry at all? And the point is, most scientists don't want to stick their neck out because they go, we're actually fairly humble and quite sort of reticent to say, you know what, I don't know, I don't know. And we're often the people that shout the loudest. And why I put this thing up about the Large Hadron Collider is that in about 2015, they were looking for the thing called the God particle or the Higgs boson. And the LHC made this big announcement saying we're going to make a big press event, and clearly they were going to make some announcement. And one of the scientists I was with, I can't remember who it was, said, I hope it's something like, because we have this prediction, and they said, we're going to find this particle within this range, it's going to look like this. And they said, I hope it's something different, And I was like, why? Like, we want to find this thing. And they were like, yeah, that'd be boring. Like, scientists, like, we want to find the chink in the armor of our theory. Like, we're always testing it. And I think that idea is really important. Like, if you show me, go, look, actually, this thing doesn't work, or this thing works like this, great, let's write a paper on it. So it's not like we're arrogant saying, like, no one wants to step forward and go, don't worry about it, it's totally fine. Like, as soon as, you switch 5G on and then there's clearly like loads of stuff going on, we're all going to go, well, bloody hell, like, that's weird, but we'll check it out. So, but based on everything I'm showing you in this talk, obviously, I have a severe leaning on the shouldn't worry about it side. Okay, so that was just ramble about this. Okay, so the coronavirus is here, and I'm inside on a Saturday night, and this is the sort of stuff that's hitting everyone's Facebook pages now. Sensationalist sort of titles. 5G is worse than coronavirus. It will be bigger than the Chernobyl disaster. And I don't really want to debunk this stuff. It's crazy stuff. But I asked the people that view this to look at the websites on YouTube and the other videos that are placed on these sites. We're going to watch a bit of this in a second, actually. Actually, I'm not sure I can play it with this setup. But the point is, on the YouTube site, they're actually selling T-shirts from some shop they've got, and all of the videos that they've got are just these sensationalist pieces. I was going to show you this video. But I don't think it'll play over the speakers. Okay, so there's a clip here. You can hear this guy talk, and he just kind of explains this really crazy theory that human beings are antennas, and the 5G is going to get in and bugger everything up and bugger up all our impulses. And based on the physics I've showed you above this, it just doesn't fit. And but it's this montage of just worrying footage put together, and really crazy stuff. And do we really need to entertain this? And there's no physics, there's no evidence. It's just a guy talking. And I want to focus actually on the personalities of these people presenting this information, because it's important to look at that as well. Okay, so let's get into the really crazy stuff. Okay, photos are not evidence, right? They're not. So if you post something on Facebook, okay, I can write anything on a photo. 5G installation guy wearing a effing hazmat radiation suit, and everyone goes, "Oh my God," blah 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 blah. And physicists go, "Oh, for God's sake!" Like, you can take any photo and twist it to suit your understanding. And if you type this into Google, it's debunked straight away. People go, "There's not a guy in a hazmat suit, doing this thing." It spreads like wildfire. The other one was the bees next to some 5G or 4G antenna, and this is really weird because it's I can't remember the video anyway. Like, I'm not even going to dig into this because this isn't evidence. This isn't how science works. This isn't how we communicate and transfer information to like other people. Like, I could take a photo of my dog sleeping on the floor and go and take a photo of an antenna and just piece them together. It's just rubbish. Just ignore it. Yeah, right. So I found a photo on the internet of this guy. So, like, I could sit up all day making crazy photos of people, and put captions over them to worry you. Did this guy start the coronavirus? Did he eat the bat? I don't know. Look at him. This seems quite weird. Why is he wearing a tuxedo and holding a sewing machine? It doesn't make sense. The point is, can I prove that he didn't start the coronavirus? Not really. Like, I can. Like, it's just, but like, there's heaps of other stuff I can't prove. So like, like a photo, if you share a photo on Facebook, just think, please, just really think about what you're doing. And this is sort of typical of this talk or lecture I've got to give, is that it kind of takes me an hour and 20 minutes to go, no, where sharing a photo is very quick and simple. And yeah, there you go. Right. So, yeah, this was the other point I wanted to make actually as well. So I've sort of been building this narrative that you shouldn't worry about 5G. But I'm going to say, stop worrying about the delivery mechanism and worry about the content, or don't shoot the 5G messenger. And I think there's a bigger picture here where we need to say there needs to be more debate about how we use our mobile phones. Do we actually need more data, and do we want 5G? That's a different topic to, is it dangerous? Okay. And I think there should be a lot more research into the longitudinal effects of exposure to Facebook and Instagram. Instagram, you're not good enough. Facebook, your friends are doing this, you're not good enough. You're going to get this. You should have this when you're older. Okay. And we already know that children are suffering from a deluge of mental health issues from just seeing this stuff, even sexualized imagery and the such like. And I think we'll see in 10 years' time a switch to education for young people to say, you don't want to be on a mobile phone, not because of the 5G, because actually what's on them. So I find mobile phones, I'm not going to stand here and say mobile phones aren't dangerous. They bloody well are. And we need to think about that narrative much more than demonizing the delivery mechanism than actually going, 5G is going to harm you, but that's fine. Your 14-year-old can watch porn. Like, it's not right. So I put up this image here. I've actually been really interested in this thing called the Light Phone, which is kind of like an iPhone killer, which does directions and contacts, text messages, and phone calls. And I think this is a fantastic idea. And I think we should move more into that direction. And I say to the people in Cornwall, I would completely support a narrative. I wouldn't say, if you don't want 5G in your neighborhood, I mean, the towers are horrible, right? if you don't want them in the spacing that they've got to be spaced out, and you're happy with 4G, you've got enough data, then that's fine. You know, work on that argument and work on the actual content with your children and the people in the community, saying, do we really, really need this? And I think that's one thing the coronavirus has sort of come to show, if you like, that, you know, there's just been this huge expansion for more data, more blah, 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 blah. And I think that's an important talking point for dealing with this pseudoscience associated with 5G. Okay, right. So the next thing I was going to say was, you're not entitled to your own opinion. And that sounds really arrogant, but I'm going to say I'm not entitled to my own opinion on everything that's not in my speciality, right? And even many things in my speciality. And there's a really great article, excuse me, I have a drink of whiskey. There's a really great article in The Conversation, which talks about the philosophy of saying you're not entitled to your own opinion. And I'll give you an example. If I take my car into a mechanic and I've got a flat tire, and he goes in and says, I take it to a mechanic, a well-educated person who spent years learning, you know, the intricacies of engineering and the such like. And I say, he looks at the car and goes, you need your tire changed. And I go, no, I'm entitled to my own opinion. I want the clutch changed. Like, if you think about what the mechanic would say, like, well, all right, mate, like, you need a new tire, but I'll change the clutch if you want. And there seems to be this switch with science where everyone seems to be able to get some information and be like, well, no, look at this YouTube clip, like I'm an expert, you know, and it's really weird. Like even when I talk to climate scientists or mathematicians, I go, look, I don't know anything about this. Can you tell me about it? And for some reason, this is broken down. And I think there's this great phrase in this piece, which says the problem with I'm entitled to my own opinion is that all too often it's used to shelter beliefs that should have been abandoned. It becomes shorthand for I can say or think or whatever I like. And by extension, continuing to argue is somehow disrespectful. And this attitude feels like, I suggest, into the false equivalence between experts and non-experts. That's an increasingly pernicious feature of our public discourse. Like, so it's basically saying that everyone's just going, I've got information now because I've got the internet, ironically over 4G or your Wi-Fi router at home. And I don't need to listen to anyone else now. You know, so it's an interesting point to think about. And I ask you to have respect. Like when I go and chat to someone in industry or in, like, I don't know, anything, someone that's coming around to help me do something electrical in my house, you know, just, you have to be respectful to their background and the education they've received in that area. Okay, so let's talk about a little bit of psychology, which is not my area, and I don't have any right to be an expert on it, really. But I started looking at this after watching that Flat Earth documentary. And I started looking at the Dunning-Kruger effect and denialism in general. And the Dunning-Kruger effect is represented by this graph here, which we should all be aware of, which is that your confidence as a function of experience, your confidence as a function of experience will typically have this peak where you go, I can do this. I know what I'm talking about. I've read a few articles, and makes you feel very confident that you know what you're doing. And then it's like, you know, and then after a period of time, you're actually not very good at this, and I need to become some sort of expert in it. And I think that most scientists, we sit down here, we just go, oh, I don't really feel like I should comment on that. Whilst other people are going, right, I've worked this all out, I know what I'm talking about. It's kind of really frustrating. And the analogy would be going, it'd be a bit weird to go, I can play the violin, you know, I've had one lesson, I'm going to go off and play the violin, I'm going to go and join an orchestra. And you go, well, that's ridiculous. All these people, you know, struggling for years to do 10,000 hours of practice to join an orchestra. So anyway, be cautious of the Dunning-Kruger effect. It's out there and it's real. And talk about denialism. There seems to be an increase in denialism, just the blatant denial of scientific facts. And there's this good book I'm really looking forward to reading. I've just bought it. How Irrational Thinking Hinders Scientific Progress, Harms the Planet and Threatens Our Lives. And some of the tenets of denialism are Conspiracy theories, dismissing the data or observation by suggesting opponents are involved in a conspiracy to suppress the truth. I'm going to cover that one in a minute, that I'm not part of the conspiracy. Cherry picking, which is important for the article that we just saw, saying, I'm going to grab all the information that's relevant to my argument and exclude everything else. False experts, paying someone like the guy we saw in the video that's saying, oh, I know what I'm talking about. What's your qualifications? You know, what have you done? I'm moving the goalpost. So as soon as I say, you need to look at this energy calculation, someone goes, what about blah, 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 blah. Whatever. You know. So any rules to counter-arguing the points that I made in this video, first need to address the physics. Like, if you think you're smart enough to go up against Einstein, the photoelectric effect, Planck's law, and you know the electromagnetic theory for reflection and transmission that's been developed over hundreds of years, sure, bring it to the table. But you need to approach this argument from that footing, because that underpins all of the technology and engineering that we've pieced together from these theories. You have to look, a counter argument has to look at the IEEE papers, because you can't dismiss them, you can't just ignore them. They're there, and people like me could just go, oof, yeah, what about this? And you can't use whataboutism or YouTube clips or images to counter this argument. You need to address the 3 points above, if you like. Right. So I've been reading this book recently, and I thought this is really interesting to compare 5G to climate change and to think about our own personal risk perception. So I'm reading this book called Don't Even Think About It, and it's why our brains are wired to ignore climate change. And I want to read you this passage from it because it's kind of really cool. And it says, why does climate change not feel dangerous? And it says, 5 years ago, this is the author, when I was living in Oxford, England, a cell phone company applied for planning permission to install a cell tower on the side of the pub. The area was full of liberal professionals of the kind that congregate in university cities. When prompted, they would agree unanimously that climate change was a serious problem and that someone should do something about it. And yet the threat of a cell tower galvanized them into immediate personal action. Within a week of the application, 200 people gathered in the local school to express their resistance to the tower, which they said was going to spread microwave radiation across the school playground. Some were determined to lay down their bodies in front of the installation van if needed. There are some interesting similarities between the issues of climate change and cell phone towers. Both threaten uncertain impacts that are drawn out long into the future, and in both cases we contribute through our consumption choices to the problem we decry. So, my neighbours that night all had cell phones in their pockets. In retrospect, I regret not calling them up during the meeting just to see what happened. However, there is one important difference. Climate change poses a vast and unparalleled threat. Cell phone towers do not. And moving on to the next page, to understand the forms of risk and how human beings perceive risk, it's been the biggest challenge with climate change, to psychologically engage people. It's actually really not I think the engineering and technology we need to solve climate change, you know, could come about or should be there. It's convincing humans that there's a threat, and human beings are used to perceiving threat in a particular way. And there's two types defined in this book here: dread risk and unknown risk. So dread risk, a sense of powerlessness in the face of involuntary and catastrophic impacts. Sorry, that whiskey's hitting home. So something that's intergenerational, irreversible, like nuclear war or getting cancer. And an unknown risk, like an anxiety that comes from the uncertainty of new and unforeseeable dangers, invisible and unprecedented, like chemtrails or 5G. So actually 5G fits really squarely into that block. It's a bit like a tiger walking into your village. You go, oh my God, there's this thing, and I'm really worried about it. And the 5G also has all these other sinister points to it, where you go, it's run by a corporation, it moves through the air and it can get into my body and do all of this stuff. But all the scientists go, I don't worry about it. So it just triggers this, dread and unknown risk in humans, where they go, I have to deal with that right now, it's immediate, like I have to do something about that. As opposed to climate change, we go, this thing's gonna happen in 50 years. It's not run by a corporation. In fact, it's argued against it from the oil companies, which is well known. And in fact, if you look at the numbers, for example, cycling is very dangerous. You're very likely to get run over in a city, but it doesn't trigger any of these dread or unknown risks. I go cycle, whatever happens if I get hit by a bus, I get hit by a bus. but you don't dread it or there's no unknowns in it, as opposed to 5G. So it's important to think about your human risk perception when you see these things on Facebook and you go, oh my God, I need to react and I've got to share this thing. And you go, oh, calm down, just go and look at the, go and look at the information on it. Okay. What else have I got here? So why am I lying? All right. If I thought 5G was an issue, I would say so. Like, I work at a university, I don't work for a telecoms company. Like, I've got nieces and nephews, my partner's pregnant. Like, I would really be going, we need to worry about this right now. And let me be really, really clear. I'm really worried about climate change. We really, really need to do something about it. And it's just impossible. People still arguing, things that are thought up by the oil companies in sort of, think tanks to convince you that it's not real. They go, well, the science is really out. And you're like, well, it's not. You've just been told that and you're regurgitating what some cheesy guy in an office has thought up to convince you not to worry about it. And to play on all of these risk perception factors that you have. So if I thought there was a problem, and if I think there's a problem in the future, I'll say so. And in fact, as a radio astronomer, it would be better for me if you actually all stopped using mobile phones, because I'd have a much clearer spectrum and I wouldn't have to get rid of what's called radio frequency interference. I'm not paid or influenced by the telecoms industry at all. And actually what's interesting for the Arza Silly case, this is the beach that's included as a picture in the petition. And here's me playing guitar on that beach, age 15, and here's another picture of the beach I took on St. Martin's, which I used to go to every year, and have friends on Facebook that that live there. So, like, it's a little bit hard to explain why I'm so passionately arguing for not worrying about this, considering that I bloody love the Isles of Scilly, and I don't really have any reason to lie. But I think we should always still be cautious, and I think what the IEEE standards are there to be, let's still be cautious about this situation, and of course monitor it and be scientists about it. So why this is really important right now, why I feel compelled to make this little film about this. There's just so much rubbish out there right now, especially coronavirus, and the 5G stuff just kicked off really badly. But I think it's important as a scientist to shout this down and go, no, don't worry about it. Here's the evidence. Here's my point of view. Because we don't do this very often. We'd like scientists just keep in their bubble and do their research. We do some outreach, but not heaps of it. And there's been some really worrying things recently. I've been pacing around the house worried about this guy, a guy up in Byron Bay, who is just a pseudoscientist who went online and said, you don't have to worry about the coronavirus. You can't catch a vaccine. Just wash your hands and you just go out into the community. And what's worrying about this guy and other people is that the R0, which is the number of times you spread this virus to someone in the community, is a local parameter. It's local to Byron Bay. And if someone convinces you, you don't need to worry about this, okay? Someone just goes online and goes, you don't need to worry about this, then that's people's lives you're putting in danger, because someone walks outside and then we know that, they're going to give this to X number of people. And you have to look at the personalities of the people presenting this stuff. What do they have to gain from it? What qualifications do they have? And seriously look at the video. And not share this stuff. Like, it's really important to go, I'm not going to share this because I'm giving this person a platform. And so my points here are, stop sharing rubbish because it harbors an alternative and incorrect idea. There's like a sheep of people going, I think all this is correct. And then there's always one person that goes, I'm just going to argue the opposite. I'm just going to do the other thing. And you're like, that's fine. But it can get a lot of momentum on Facebook for being incorrect. And this is very worrying right now, because 5G, I don't really care that much. Like, if you want to put tinfoil around your head and go and protest in the street, whatever, like, it doesn't really impact anything. But the sharing of this information and the worrying about it distracts us from other important things like climate change and how to solve the coronavirus issue right now. And I bet these people, as soon as the vaccine will come out, they go, don't take it. You only need a few people to go, I'm with them, okay? They're not scientists, they're just going to say it, and you've got an explosion of cases on your hands. Now, I ask you to look at, you might not be a psychologist, but some statistics I've pulled off the internet, 0.5 to 1% of people show some level of narcissistic personality disorder. These people want to be on television. They don't care if your comments are negative or positive. They just want to get comments on their video. That's what they're out there to do, and you need to understand that. And you know, they're making arguments like all scientists are wrong, I'm correct. Like, really just have a think about it and just go, do I want to give this person a platform and share their views to push this more out into the community? So that's kind of why I wanted to make the video today, because I don't think scientists speak up enough and say, look, that's just rubbish. Don't worry about it. So my last slide is here. So should you be wearing tinfoils on your head? No. But put sunscreen on, okay? When you go to the beach, put sunscreen on, because UV radiation causes cancer. And stop sharing crap. Thank you.